Okay, so let's start. So last time we studied Gaussian mixture model. So Gaussian mixture model is composed, basically the algorithm to fit the Gaussian mixture model is composed of two steps, which is done iterative manner. The first step is to compute the something called a posterior probability. So for this particular point, what is the probability of belonging to this Gaussian or this Gaussian, right? And that, how do we compute this posterior probability? Is by computing the likelihood of belonging to the first, each of the Gaussian component, but we multiply it with the prior value, right? The prior probability. So initially we kind of have, so when talking about the prior in the context of Bayesian probability and Bayesian statistics, it's about some kind of bias, okay? In a wrong, in a kind of bad or undesirable sense, bias means some kind of prejudice, okay, which is some kind of our prior belief with no ground or no evidences. So without seeing anything, we kind of have a prior knowledge or some kind of biases or prejudice of seeing the data point from here with a higher probability of, for example, like a 70% and the 30%, right? And then we compute the probability of generating this point from this Gaussian, right? And then that Gaussian, the likelihood value, which means the probability of generating this point from this particular Gaussian component. So that was something like 0.05. And then we multiply them together. And then from this Gaussian, with the center here and the variance or covariance here, and the density or the probability of generating this point from this Gaussian was 0.10. Okay, and then in that case, overall is 0.7 and 0.05, and then 0.035, and then here is 0.03, right? So that way, 0.035 and then 0.03. So the ratio between these two, and then normalizing them so that their sum is becomes 1. So that will become the posterior probability, right? So this is the one of the two steps, and then the second step is to estimate the parameter of Gaussians. Each Gaussian component, which is mean and covariance values, right? And then that's nothing but just the weighted sum of all these points with respect to this posterior value, and also we compute the covariance values in a similar manner. So okay, so the mean value for each Gaussian component is computed as the weighted value, where the weight is our posterior value of each, and then multiplied by each point. So we involve all the points to compute each of the Gaussian mean value. And also the covariance matrix is also computed in the similar manner. So we use the mean of each component, and then every data point is participating in computing this covariance value. And then in general, these kind of optimization scheme is called what? E and M combined together, we call them as EM algorithm. Okay, so EM algorithm is basically you can, if you're familiar with the maximum likelihood estimation. This EM algorithm is a kind of extended version of a maximum likelihood estimation. But in order to compute the maximum, so basically what is the role of maximum likelihood algorithm? So given our data, we want to find or estimate our parameters given our data that maximizes the probability of seeing our data, right? So that is the main kind of process done in this maximum likelihood estimation. So here in this EM algorithm, this M step is exactly doing the maximum likelihood estimation, which determines our parameter value. But what is this E step? What is this E step? So in E step, so among our observation, so if we observed, if we observed a person's height, and then that height was 175, 173, 169, and so on. So these are our data. But additionally, we assume that there are some unknown observations or some unknown information that are associated with each of our observation values. So that way we kind of categorized the observations or observed variables into two, which is observed one or unobserved one. And so these unobserved one has to be estimated. So that way we can complete or we can have a kind of full information by just filling up unknown pieces of an information. So filling up these unknown information among our observation, okay, so that is called this E step. So in this particular case, what is the unknown observation? So that unknown observation is just a posterior probability. So if someone told you, okay, so this guy was generated from this Gaussian, or this guy has the posterior of being generated from here and here as 60 or 40. So if someone gave you this additional information, which will form the part of our complete observation, okay? So this is some unknown unknown portion of our observation. So filling that kind of part is called this E step or expectation step. Okay, so altogether we just iterate between these two. So that is the main kind of process done in this EM algorithm. And this is a really nice. This has a really nice theory. So so it will take a lot of time to just go through them in detail, but I'm gonna just give you kind of high-level ideas. So, and then also in case you study those topics, and then you will see those terms called incomplete likelihood, or complete likelihood. Okay, so this complete likelihood is when is the likelihood function when you completed filling up the unknown information or latent variable or latent observation. And then this incomplete likelihood is the likelihood function before you filled up those unknown information. And that unknown information is typically called latent variable or latent random variable. Okay. So if you have a chance, I strongly encourage studying in more detail about this topic, because it's really backed by really nice theory. And it has been applied in a wide variety of applications, including many of other engineering field and also computer science fields as well. Okay, so if you heard about LDA, latent Dirichlet allocation, or any other Bayesian models should be solved, or we have to have this kind of EM algorithm to handle or to solve for any type of Bayesian networks or Bayesian kind of statistics, because in the Bayesian case, we assume some kind of prior. So we have some prior and then some latent variables that becomes typically our parameter sets, and then these random variables will finally generate our observation. So we only know about this part. So these unknown random variables has to be naturally introduced in the case of a Bayesian setting. And so in this case, we typically have to involve or have to utilize this EM algorithm or this kind of framework. Okay. Okay, any questions so far? Okay, and then let's look into it. Potential problems or issues when using a Gaussian mixture model. So if you use a more number of Gaussian components than needed, and then you will have this kind of empty Gaussians. And if you use a smaller Gaussians than needed, and then you might have this undesirable result. And then also this problem is another big problem, singularities. So in this case, if I have chance, and then I'll prepare for some homework that you can play with the Gaussian component and training those Gaussian components. And so although it's backed by really theoretically deep EM algorithms, but all the intuitions were explained, and I think if you followed my explanation last time, and then I think you have no problem just implementing those Gaussian optimization of this Gaussian component by just computing the posterior and then computing the prior and also estimating the parameter values. So you just either iterate them, but sometimes depending on the initialization, or if you have excessively large number of Gaussian components, and then you might see some Gaussian some likelihood values as like infinity of Gaussian mixture. I mean the likelihood values. So in this EM algorithm is basically optimization algorithm. So what are we optimizing? So we are trying to maximize the likelihood, right? And then in the case of a maximum likelihood estimation, it is just computed by just one single step, okay? So if we have 170, 168, 173, 180, for example, if we had this 4 components, what is the maximum likelihood estimation if we use a one Gaussian, or if we assume one single Gaussian distribution for these data? And then we can easily come up with the estimate for the optimal mean value and the variance value. And then what is that estimation, or what is that estimated parameter optimizing? So that objective criteria is basically the likelihood. So likelihood is something like this. So we may have, depending on the Gaussian mean and the variance, and then we may have this Gaussian, or maybe this Gaussian, or this Gaussian, and so on. And then suppose our observation is located around here, 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 here. And then if we assume our underlying Gaussian model is this blue, then the Gaussian, the likelihood is just the product or the multiplication of these 4 values, or multiplying all these 4 probability values. If we used this blue Gaussian, and then if we used this red Gaussian, and then we may have also another product or another multiplication of these 4 numbers, coming from this graph. And then what is the optimal mean value and the sigma squared that determines this shape that maximizes the product of all these four probability of all these four observations. Okay, so that is what we are optimizing, or that is the objective criteria that determines optimal mu and the sigma squared. Okay, so that is what we are doing. But in the case of this single Gaussian component, it is just one-step process. So by using one single formula, we can just reach the maximal point or maximum possible value of our product of all these four Gaussian density values. In the case of EM algorithm, you can view it as a kind of monotonic increase, or you can view it as a kind of gradient descent kind of steps. So we gradually maximize or improve this kind of the likelihood function or likelihood value. I mean the product of the likelihood value from all the observations that we have. Okay, so we are monotonically increasing or optimizing our likelihood functions or likelihood value. Okay, so in this case, if we follow these two EM steps iteratively, so if we do one step at a time and then iterate them, and then that will monotonically increase our likelihood product or product of all these likelihood values of these points. And then if you monitor those Gaussian, the likelihood value, and then since it is a really small value, we typically use a log versions of the Gaussian value. So instead of using multiplication of or the product of all these four values, we just use the summation of the log fxi, for example. This fxi is corresponding to this Gaussian value, right? Okay, so so if you observe this value when just implementing the Gaussian mixture model, and then this should go up, right? This should monotonically increase, but sometimes you may see infinite value as this Gaussian, this likelihood value. So it means your likelihood value became infinity, which is really the maximum possible value, right? So that is really happening. And so in that case, how can we interpret that? So if our function is something like this, and then we have to find, I mean, if we want to maximize this function, we have to find this point. We have to reach this point, right? But the fact that we can see the infinite value of this likelihood function, it is something like this. So at some point or at some parameter value, we see the infinite value of our Gaussian, our likelihood value. So in that case, theoretically, it could be our solution, but is often giving just a meaningless result. And that meaningless result is really made or can be created or formed by just assigning one data item. So if we had 4 data points, and then if we had a Gaussian probability that is all assigned to this point, something like this. And then even though all the other values are really small, but we can assign really high density value to this particular point. Okay, so in this case, the Gaussian is just considering or taking into account just a single point. So each Gaussian component, if we use maybe 3 Gaussian components, and then each of the 3 Gaussian components should reflect multiple data points. That is corresponding to each of the 3 clusters. But in some cases, the Gaussian is only just focusing or emphasizing just one data point. Okay, So in that case, the sigma will become 0, which means this Gaussian distribution, one of the Gaussian component, 3 Gaussian components, become narrower and narrower. Okay, so that way the density value or the likelihood value assigned to this this single point will give you already infinite value of our likelihood value. Okay, so in that case, yeah, it is certainly not the best case. So we have to avoid this kind of situation. So sometimes in practice, if you use a different initialization, then you might see this kind of result. And so in this case, this kind of optimal value or this optimal Gaussian value is this, but sometimes one Gaussian is just like this, yeah, really narrow bandwidth or the sigma value, which is really small. So that is sometimes happening. So yeah, so in that case, you have to use a different initialization, or you may be able to regularize your covariance matrix. Yeah, but yeah, there are some other tricks, but yeah, I'll just mention it at this level. Okay, then let me go back to this figure. And then let me just discuss just a few differences between the Gaussian mixture model and the k-means. So if you if you formulate the k-means algorithm, and then it can be viewed as also a Gaussian mixture model. And so in that sense, we have to figure out, or we have to understand what are really differences between the k-means and also Gaussian mixture model. So yeah, as I mentioned in the last lecture, so Gaussian mixture is kind of a soft version of a k-means, right? So if this point was closer to this than to this, and then it will be assigned with 100% to this Gaussian component or this cluster, right? So it's like a 100 versus 0%, right? But also, yeah, what is determining factor of assigning this to this Gaussian? It is based on which one is a shorter distance, right? Which one is closer, right? But in the case of a Gaussian mixture model, the fact that we have this skewed or this kind of a weird covariance shape actually plays a role of distorting our distances. So in this case, as I mentioned last time, so all these points along this circle will have the likelihood value of, for example, 0.1. And then this guy is also will be the point that have the probability of having 0.1. So in that case, they can be considered as having the same distance, right? The same distance. So if we consider this, and then which Gaussian does this guy belong to? It is actually depending on, it is not depending on the actual distances as it is, but this is considering, or this is taking into account this kind of weird shape. So along this direction, the distance or the probability will decrease much faster, right, than this direction. So in this case, we have to consider like this kind of contour shape. Okay, so this point is, the distance should be computed with respect to this distortion using this Gaussian or this Gaussian. Okay. So I'm just explaining it very vaguely, but so in the 1D case, if we use this really sharp Gaussian and then also this wide Gaussian, I'm just saying this difference. So suppose this was 5 and then 15, and then the middle point exact middle point will be 10. So in this case, this is not kind of equidistant point with respect to their probability values. So in this case, you will have much larger probability for the second component than in the first component. So this in this case, this point will actually have the same probability between these two Gaussian components, right? And then, yeah, this kind of circle is something like this. So the 1 and the 2 and 3 and so on. In this case, the first Gaussian, the contour and the second contour, and the third contour, which is really large. So it gets a little bit messy, but yeah. So it's like how fast your probability will decrease with respect to the actual distances. Okay. Okay. So when computing the distance or the probability of this guy with respect to this Gaussian, and then if it is sharply decreasing, and then you have to take into account that. And so also using this, you also have to take into the account this kind of different rate or velocity of decreasing the probability values, because they have different covariance values. Okay, then also another thing. So suppose we had exactly at this point. So one point is exactly placed at this point, which will have the same density value between these two Gaussian components. But this one is not a equidistant point. I mean, so we have to we have to consider additional thing when actually, so this is a kind of break-even point. So if the point is on the right of this point, and then it will become, or it will be assigned to the second Gaussian, or the Gaussian on the right. And then if we have point here, and then it will be assigned to this Gaussian. But we have to also consider additional thing when discussing this kind of break-even point. Okay, that additional thing is prior. Okay, so as I mentioned, so even though one Gaussian is really sharp and the other is really wide, but we have to consider the prior value. So prior is so initially this Gaussian and the area around here, and then the area under this Gaussian will all be equal to 1, because both of them are just one single Gaussian distribution, right? But we have to multiply the prior probability assigned to each of the Gaussian values. So if this guy has the probability of 0.7, 0.3, and then 0.7, and then we have to boost up this, okay, with the probability of 0.7 and 0.3. So that way, you are giving kind of unfair biases to this Gaussian with this amount compared to this amount, okay? So in that case, this break-even point will be moved to the left. Okay? 그러니까 이게 더 가중치가 크니까요. 그러니까 얘가 이제 0.7배 이렇게 올라가고 얘는 0.3배 올라가서 이 브레이크-이븐 포인트가 얘 그래프가 더 올라가니까 상대적으로 2.5배만큼. 그래서 이제 이 브레이크-이븐 포인트가 더 1로 가게 됩니다. Okay, so we are giving like 2 times 5, yeah, like 7/3 more probabilities to this guy, right? So this graph on the right will be boosted or increased overall, and so this break-even point will be further moved to the left. Okay. So that way, I keep using this figure. What about the k-means and the like which one will belong? I mean, which Gaussian component will each data point belongs to? I mean, in the case of k-means, we are using just Euclidean distances, just in an equal manner. So we are kind of fair between each Gaussian or each centroid or each cluster component. So it will be exactly, so if these two were our centroid, we will exactly split our spaces into these two, right? But in the case of Gaussian mixture model, we are distorting this distance computation or how we compute this probability using this its own shape of a covariance matrix, okay, for each Gaussian, and then also we apply some prior values onto each of these Gaussian components. So in terms of the break-even region, or it can be viewed as a kind of separating hyperplane in the context of classification. Okay, so which data point will have larger probability or larger posterior values to one Gaussian? It may have some weird shape. So in this particular shape, it can be something like this, but also it can be further moved to this. Okay, so in this case, we are giving more prior to this guy, and then also this guy has a wider probability that can cover, or that has a slow decreasing rate, okay, in terms of the probability. So in that case, yeah, it might like eat up our spaces, okay, unfairly, okay. So this is yeah, this can be viewed some additional algorithm flexibility, okay. So that can be viewed as a high variance of our model in terms of a bias variance trade-off. Okay. Okay, and then yeah. So how can we regularize this model? How can we regularize this model? I mean, yeah, it may be too flexible. I mean, it may be too much of a flexibility that we give to our model. So it can be really unfair, right? Because we made our model quite flexible. So in this case, one simple thing is we can just, I'm talking about the possible regularization. So in order to remove this kind of unfairness, one thing that we can do is to remove this prior values. So we do not infer the prior probability based on the data items of posterior. We are just imposing the exact same prior values onto each of the Gaussian components. Okay, so in that case, we just give a 0.5 and then 0.5 as the prior probability to each of the Gaussian. Okay, and then how can we regularize this weird shape in terms of different rate of decreasing the probability with respect to the distances? So how can we do that? What is the way? What is possible way? Okay, then, yeah, let me ask a kind of simpler version of question. So, so we have this red or this green ellipse, right? That can be any shape, but we want to have this kind of circular shape. I mean, exact circle. In that case, how can we do that? So, what is the corresponding covariance matrix? Identity matrix? Right, yeah. Okay, so for this Gaussian component, so the student mentioned that we can restrict or we can regularize the covariance matrix as just diagonal matrix. Okay, so we are assuming just the full matrix. I mean, any type of a matrix of our covariance matrix, and then it can be any shape of this ellipse, but we can restrict our matrix as this first diagonal matrix. For example, 3 or 5, and then 0. So in that case, what would be the shape of this ellipse? This ellipse will be either horizontal or vertical, right? So in this case, let's see. So let's see. So would it be this shape or this shape? Which one is corresponding to this? 3 and 5. Like this short and fat or tall and skinny? Skinny one, right? Which means, yeah, if you think about the variance, and then in this graph, if the variance gets larger, and then it will have a slow rate or slow velocity of decreasing the probability, right? So if we have large covariance value, and then this is corresponding to the y-axis, okay? So in that case, we are having this skinny or tall covariance matrix. So along the y direction or this vertical direction, the probability will decrease very slowly. Okay, then, okay, so this is one version of regularizing our Gaussian mixture. And then the other version, it will be having this, the multiple of identity matrix. Okay, so 1, 0, 0, 1 times some variance, which is a common to every dimension. So in that case, we can restrict the covariance matrix as just a circle. Okay, so that way we can restrict the velocity to be the same in every direction, in all directions. Okay, so that is the meaning of this spherical covariance matrix. And then still in this case, we can use this variance value as our parameter to estimate. Okay, in that case, each Gaussian component will have its own parameter value here, and then this Gaussian will have 1, 0, 0, 1, and then sigma squared, yeah, sigma 2 squared. So in this case, still we are allowing some unfairness. So this Gaussian will have some large covariance matrix, but this Gaussian may have much smaller covariance matrix, although they are all in all circles. Okay, so this is a kind of another version of a regularization to this Gaussian mixture model. And then we can, yeah, the most restricted version of the Gaussian mixture model would be just to use the same or the common Gaussian variance parameters for each of these Gaussians. So regardless of any Gaussians, we are assuming the exact same circle as a covariance for each of our Gaussian values. Okay?
그러면은 그냥 거리에 따라서 가까운 걸로
네, 그러니까 이거 같은 경우는요, K-means랑 이제 거의 같아져요. So in this case, as the student pointed out, it will become just as a K-means. Okay, although K-means is just only allowing 100% versus 0, but still, even if this is our separating separating boundaries, but still for this point we are using some kind of soft posterior probability values to each of these assigned to each of these Gaussians. Okay, and yeah, I think that's it for Gaussian mixture model for what I wanted to discuss. So any questions? Yeah, so my explanation might be kind of too high level, so it may not be easy to understand, but yeah, I think yeah, if you try to implement this Gaussian mixture model using a different versions of a regularizer, such as what I just mentioned, like a diagonal Gaussians or multiples of identity matrix or exact common Gaussian covariances among all the Gaussian components, and then you will see the differences between them. Yeah, and any questions? Okay, then the next clustering algorithm that we will cover is called this DB-scan. So let's see. Let's check the 보자. 아버지 할 수 있어.
비주얼
I realize my students' lab is just outside, so we can use this nice Wi-Fi. I hope it connects. 멀어서 잘 안 되나? 네, 네, 아까 뭐 안 되는 것 같아갖고. Maybe I just try to use Korea Univ AP. So I just wanted to show how many cited. I mean, how many this paper was cited, and also some image searches that we can get a take a glance on this method. So it's a pretty old method for the clustering method, but it's been really popular method in old days. I think it's still quite effective, especially some low dimensional data. So it's not, this one can be viewed as one good research example. Okay, so so DB-scan is having the name of this density-based clustering. So let me describe this algorithm just one by one. I mean from the bottom to top. So let me just use this example. So first of all, in order to design this algorithm, it just defines some different types of points. So the first type of points is called this core point. And then in order to compute this core point, we have to have a two parameter, which are the main parameters in this algorithm, which are this epsilon and the mean number of points. Okay, and epsilon is, you can think of it as just a kind of threshold distances. So suppose that distance was 1 centimeter, for example. Okay, so instead of this weird the unit of this unit, but let's just think about this threshold as a 1 centimeter, and then this mean point is used here. So you pick up 1 point in your data, and then you think about this hypersphere that is having the radius of 1 centimeter. Okay, and then you can think about this hypersphere in the original space, and then you count the number of points belonging to that sphere, and then if that number of points, including that point itself, if that number is greater than or equal to this mean number of points, which is another threshold in terms of the number of points, and then we call this point as core point. Okay, so core point means some point that is in really dense area. Okay, so that's the meaning of the core point. Okay, and then the border point is this. Border point is the actually the neighbor of this core point. So by the neighbor, I mean that the neighbor is defined within this epsilon distance, or 1 centimeter. Okay, so we also consider its one radius of 1 centimeter hypersphere, and you can see one point as a core point. Okay, so you have the neighbor as a you have the core point as your neighbor point, but you are not core point yourself. Okay, which means within your circle you don't contain this many number of points. So in that case, it is called a border point. And then, yeah, you can understand it in the following manner. So let's think about really dense regions of points, and then the dense regions are becoming more sparse and sparse. So as we get outside, as we get more and more outside, then we see a less and less number of points. Okay, in that case, we will see some core points around up to around this part, but after then you will see some points that are not core point, but which are connected to this core point. Okay, so that is a kind of an intuitive understanding of this border point, which will form some border of these dense regions.
그러면 골든 포인트가 이렇게 원이 있으면 거기 안에 들어가 있는 게 코어가 한 개가 들어가 있어요.
네. 그렇지만 네.
저기서 저 하나가 지금 코어가 아니죠.
예요? 아니면 예?
얘가 보여도 그 밑에가 이제 코어가 되어 있게.
그렇죠.
예.
예, 4개요?
5개.
네. 대충 이게 아마도 이렇게 그려지지 않을까 싶고. So the question is, does this guy really have a core point as its neighbor? So I guess this point will have the core point. Okay. So if we draw this hypersphere, I guess it should have like 4 other points, and then adding myself, and then it will have a 5 point in total. Okay. Then what is the outlier? Outlier is really simple. Outlier is neither core or nor border point. Okay, so that is outlier. So yeah, it doesn't have enough number of points nearby, and also it's not connected to the core point. Okay. Then using these concepts, we define this epsilon neighborhood. Okay, epsilon neighborhood. Okay, so epsilon neighborhood is, just a neighborhood relationship that are placed within the distance of an epsilon. Okay, but see. Okay, let me just move to the next concept, which is this reachability. Okay, then directly density reachable, and this is okay. So this becomes this is actually has the same definition of this border point or the core point. Okay, so that is a particular point is directly density reachable if it has the neighbors within 1 centimeter circle or hypersphere, which is core point. Okay, so the definition is almost the same as this border point, but we are now defining the relationship between them. Okay, so directly density reachable means you have a neighbor within 1 centimeter, and that point is core point. Okay. Okay, and so one interesting thing here is it is not a symmetric relationship. So if P is directly density reachable from Q, even if that is true, but Q may not necessarily directly density reachable from P, right? So it is obvious, right? So if this is a core point and this is a border point, so this guy is directly density reachable from this point. So P and Q, okay? But this P is not directly density reachable from any other point, okay? So it means it doesn't have any other core points, okay? Or we are talking about the relationship, pairwise relationship between P and Q. So if Q is not a core point, and then P is not directly density reachable from Q, because Q is simply not a core point. Okay? So far so good? And then now we remove directly here, and then we talk about density reachable.
Okay. 아까 거
네.
잘 이해가 안 되는.
네.
그럼 코어 포인트에서의 거리만 측정하는 거, 코어 포인트 자체는 그 다이렉트 덴시티 리처블이 안 된다 이 말씀이신 건가요?
코어 포인트 자체는 그러니까 누군가 다른 사람을 따져야 되고요. 그 다른 사람이 코어고 이 사람의 거리가, 그러니까 나와 이 사람의 거리가 1cm 미만이면 이제 내가 저기로부터 directly density reachable 한대.
그러니까 결국 기준이 코어 포인트여야 된다.
네.
이건 거죠.
Okay, so to be clear, so when talking about P and Q, so if P is directly density reachable from Q, and then we have to satisfy the fact that Q is core point. Okay. Okay, and then the next concept is the density reachable, which is a kind of removing directly. Okay. In that case, it is. We basically consider the chains. So we consider P and Q, and then let's see if P is not directly, but P is just density reachable from Q. Okay, so we just removed directly here, and in that case, Q should be the core point, right? As I mentioned in the previous example, so this guy should be core point. And then P is not direct neighbor of Q. So in that case, this guy, for example, is directly density reachable from Q because Q is a core point, and then this guy is inside of the circle of the radius of 1 centimeter. Okay, and then we basically consider the chains starting from here and then arriving at this point, and then all the points in the middle, all of them should be core point, and then also between the adjacent points, they should be within the neighborhood relationships. Okay, so this guy is core point and this guy is a core point, and then we can actually extend this kind of chains, and then we consider this radius, and then we can, for example, move on to this point if this P is not yet inside of the circle of 1 centimeter. Then also suppose this guy is also a core point. Okay, and then this guy P is a neighborhood of this point, and also this guy is also the core point. Okay, so if we think about this core, and then the last point, okay, and then in that case, P is density reachable from Q. Okay, so intuitively, this kind of concept is used for, let's see, maybe I have removed it, but so you have really dense regions here, and then a little bit less dense regions around here. But in order to, so it's like, so if you see the pseudocode or how the overall algorithm works, then it's like starting from one single point, and then you are iteratively expanding your cluster from that single point. Okay, and how you expand the cluster starting from that seed point is through this density reachable kind of a notion. So in order to have this cluster to be belong to the cluster starting from one of the core points here, we have to find some density reachable root, okay, arriving at this point. Okay, so intuitively we may be able to see some loose connections which are all border points. Okay, so we may not see any core point in the middle of these roots. Okay, so in that case, those 2 points cannot be connected or merged. It cannot be merged into one cluster. Okay. Okay, then let's see. Okay, so this density reachable is not also a symmetric measure. So even if Q is density reachable from Q, but the direction may not always be reversed, right? Because from the beginning, Q may be your border point, so it may not even make sense to start with the border point. Okay. Okay, so in that sense, they are not. They are not symmetric kind of a concept. And now we think about this density connectivity. Okay, so density connectivity is a kind of a more generalized or relaxed version of this density reachable. So we started from directly density reachable and now we talk about density connected or density connectivity. Okay, so in this case, we now finally talk about the relationships between the border points. So suppose you started from really dense regions in the middle. Okay, in that case, suppose this guy is one of your core point, and then you just hop around until you arrive at one of these points, which is a density reachable relationship. Okay, so it can be a border point or it may be just another core point. So you reach it here through density reachable relationships, and then you go to this direction and then arrive at here, which is another point, which is a density reachable starting from this point. Okay, and then density connected means you consider these 2 points, P and Q. And then if those 2 points have the same kind of parent, okay, same starting point, which is one of your core points, right? And then starting from this point, until arriving at one of your points, you have a density reachable, and then another point is also density reachable from the same point, and then you are saying those 2 points are density connected. Okay. So in this case, this density connectivity or density connected, being density connected, is now finally kind of symmetric relationships. Okay, because you only need to find some common parent, okay, which is one of your starting point as a core point.
저거는
네.
O는 코어여야 되는 거고 지금
네.
시메트릭한 관계.
네, 맞아요. 이게 여기 노테이션이 좀 잘못됐어요. So there is a typo here. So we don't see any R in this slide. So that should be O. Okay. So up to this point, we now have a really nicely designed building block. So I think personally, I think this is a really good example of research. So you are defining really small concepts from the bottom, and then you build from those small concepts, coming up with a really nicely designed algorithm. And all the steps from the beginning is really designed in a principled manner. Okay, then we now define the notion of the cluster. So cluster means basically a set of the data sets or the data points, basically a subset of the data points. Okay, so which we know just typically as say clusters, and the cluster should satisfy the two constraints or two conditions. The first one is maximality, and then the other one is this connectivity. So so it is something like this. So so if you have 100 points and then you claim maybe 5 of them are one cluster from the definition or satisfying the cluster defined in this DBSCAN, and then this should be the maximum cluster in a sense that we have to satisfy the first condition. And, let's look at this first condition. For all PQ, if P is in your cluster and then Q is density reachable, which is a kind of strict concept, right? Then compared to density connected, right? So if Q, if you see some point Q, which is a density reachable, but this point is not yet belonging to your cluster, and then your cluster should contain that point as well. So you cannot exclude the point that are density reachable starting from one of your clusters. Okay. So that way, you have to maximally expand your clusters. Okay. So that at least you have to contain all the density reachable points from the existing point in this cluster. Okay, and then the next one is connectivity. So connectivity means for all the P and Q which are currently contained in your cluster. both of them, any pair of these points should be densely connected, which means you pick up any pair of the points in your current cluster, and then you should be able to find the common parent node that are densely reachable, starting from that point to each of your points. Okay, so that way you are expanding your cluster maximally, but at the same time you have to maintain the least level of a connectivity or kind of tightness or cohesiveness within your cluster. Okay, so that is kind of guaranteeing some quality of our clusters. So those two concepts are also really nicely defined as a kind of constraint or condition to satisfy that your cluster should satisfy. And then there are some other data points which are called the noise, which are not directly densely reachable from at least one core point. Okay, so any point that doesn't have the neighbors as a core point. Okay, so for one point we consider its neighbors, and none of them is a core point, and then all these data points are noise points. Okay, so these are not included in any of the resulting cluster in this algorithm. Okay, and then the it's almost all. Yeah, that's about it for almost the describing this algorithm of this dbScan. So algorithm is really simple. So we just pick up any point which were not assigned to any of the existing clusters, and then we construct our clusters gradually. Okay, so we start from one data point, and then that should be the core point. Okay, and then you actually identify those points that are directly densely reachable. Okay, and then if those points are your core point, and then you can imagine some algorithms like depth first search. Is it a breadth first search or depth first search? So you start with the one core point, and then you identify all the neighborhood, and then among the neighborhood you identify if that point is just a border point, okay, which doesn't have enough number of points, and then you just stop there for that point, and then for another neighbor point which is identified as another core point, and then you go deeper. Okay, you crawl or collect its neighbors as well. Okay, so that way you expand your cluster starting from one data point. Okay, and then you can consider the set of your point. I mean, I'm talking about the set as a data structure. And then you basically remove the data point from your set, and then you iterate this kind of process until you make the set empty. So if you see noise point, and then you just throw away. Okay, and then if you find some border point, you leave it just as it is, because it will be eventually picked up by one of the core points, right? So that way you do, grow or expand one clusters until no other points can be added, and then this is one of your resulting cluster, one final cluster, and then you pick up another core point, and then do this same process. Okay, and then it will be your next point, next cluster.
근데 그 노이즈랑 그다음에 포드 포인트랑 그 당시에 뭐죠?
알 수 있지 않을까요? 왜냐면 노이즈 포인트는 일단 주변에 이제 네이버를 따졌을 때 개수가 5개 이하다 그러면은 그 다음에 이제 그 주변에 있는 애들, 그러니까 3개가 있었다, 5개를 만족해야 되는데 3개밖에 없었다. 그럼 하나하나들이 각자의 네이버들을 보고 5개가 있는 포인트가 하나라도 있으면 얘가 자기 자신이 이제 네이버가 되고 보더 포인트가 되고, 얘들도 다 그게 만족이 안 된다. 그럼 얘는 이제 노이즈 포인트가 되고요. So this is a high-level overview of this DB-scan algorithm. And I think you guys have the idea about how this works. And these are the results. So here we used the radius as 10 and then the minimum points as 4. And then here, so these are the classification of each point in terms of core, border, and the outlier or noise point. Okay, so in these cases, they are not belonging to any of the clusters. And then we see some border points, and really at the borders of a particular cluster. Okay, and yeah, don't get confused because all the green clusters are not saying they are all the same clusters. So they are probably one cluster here, and then the other cluster here, and the other here, right? So that's how we form different clusters. Okay. Okay. Yeah, we see the results here. Okay. 보더 클러스터라는 보더를 따로 분류를 하는 이유는 보더에서 더 못 가게 하려는 거예요. 아까 그 density reachable에서 so the question is why do we consider the border point? So between the border and the core point, I mean the difference is we can go beyond or we can keep extending our clusters from the core point. But in the case of border point, that will be assigned or included in our cluster. But we have to stop there. So we cannot further extend from that border point because we see less kind of density. Okay, kind of insufficient density values around that point. So that's when we stop growing the clusters along that direction. Okay, I'll keep discussing about this algorithm after maybe 10-minute break.
아까 expectation step에서
네.
업적으로 안 된 데이터를 캐치한다고 그랬잖아요. 그거랑 세미 슈퍼바이저랑 러닝이라는 게 있는 것 같은데 그거랑
네, 아마도 조금 다른 걸 것 같아요. 그러니까 이게 데이터들이 100개가 있으면요. 100개에 대해서 뭔가 예를 들면 이런 거거든요. 키라는 거를 다 알고 있고 여기 EM 알고리즘 쪽에서 하는 이야기는 얘네들 키라는 요소가 지역에 따라서 좀 차이가 날 거다. 그러니까 뭐 180인 사람이 이게 서울 지역에서 나타나는 180이냐 아니면 이게 예를 들면 뭐 부산 지역에서 나타나는 180이냐 어느 지역 그러니까 지역에 따라서 어떤 키의 차이가 있다라고 보고 그래서 내부적으로 저희가 모르지만 뭔가 말 그대로 히든 배리어 각각의 데이터 아이템에 속해져 있는 그러니까 그런 것들을 저희가 이제 레이턴트 배리어이자 EM 알고리즘에서 좀 이렇게 좀 개스를 해갖고 찾아내려고 하는 거고요. 세미 슈퍼바이즈 러닝은 이게 어떤 식으로 되냐면 이제 보통 클래시피케이션에서라고 한다면 몇 개의 데이터 아이템에서 예를 들면 전체 이게 다 학습에 사용하는 데이터라 그러면 이게 하나하나에 예를 들면 얘가 특정 질병이 있느냐 없느냐에 대한 바이너리 레이블을 다 알고 있어야 된다라고 했다면 그거를 일부는 좀 모르는 거예요. 모르는데 얘네들도 내부적으로 니네가 알아서 얘네들이 뭔가 그 레이블이 있는 거를 니네들이 알아서 내부적으로 판단해서 걔네들도 역시 학습에 사용을 해라라고 하는 게 세미 슈퍼바이즈 러닝.
그럼 만약에 세미 슈퍼바이저에서 레이블을 관계로 추출을 넣으면 결국 저거하고 비슷한 개념이 되는 거예요.
그러니까 이게 약간 이런 거 같은데요. 이제 데이터가 100개가 있다. 그러면 얘네들에 대한 이제 피처들을 이렇게 알고 있는데, 그러니까 레이블들을 알고 있는데 이제 이만큼은 모르고 이만큼은 알고 있어요. 그러면 이거는 세미 슈퍼바이즈 세팅이고요. 이거는 다 알고 있어요. 다 알고 있는데 알고리즘 내부적으로 얘네들의 필요로 하는 뭔가 이제 관련 정보들이 더 필요한 거죠. 그러니까 키는 알려져 있지만 그 사람 하나하나가 어느 지역에서 나타났는지 그 지역 자체는 우리가 모를 때, 그래서 그 지역을 우리가 그러니까 좀 이렇게 추측을 해갖고 그걸 내부적으로 모델에서 사용을 하자. 그게 약간 EM 알고리즘. 네.
그럼 라벨들은 다 돼 있는 거네요.
그렇죠. 그러니까 observed variable은 이제 모든 데이터에 다
object variable하고
네, unobserved 혹은 latent variable. 네. 네.
적었어도 되는데 너무 느려서 데이터마다 근데 그런 것도 있어요. 데이터마다 같은 걸 아니면 관계가 많은데 모든 데이터가 그러다가 하면
아, 네, 그래요.
저 감기 걸린 거
BPTC 얼마나 안 돼가지고
그렇게 따지면 나 맨날
한번 받으면 뭐 치료가 안 돼.
안 생기는 게 설정하는
이게 A하고 B가 다르다라는 것을
네.
이제 선배랑
네.
얘기했어.
네.
네.
그래요?
지금 그건 엔트리가 안 될 것 같아가지고
그래요?
일단은 받아서 오늘 저녁에 돌려보세요.
네. Okay, let's start. Okay, so this algorithm, although it sounds like an interesting idea built from interesting definitions of all the various notions and the concepts. But the main problem of this algorithm is that it's sensitive to the algorithm parameters. So we have two parameters, mean points and epsilon, which is specifying like the length of our radius. Yeah, so depending on these parameters, so in this case, so in general, they are like, sensitive to these parameters, and also more importantly, one thing that we have to think about when running this algorithm is, this assumes kind of the same quality of the density. I mean, the same degree of the density to form a clusters. So in this case, so let's look at this example. And then our intuition says we have to have one cluster second and the third, and then fourth, and fifth and sixth, right? But the problem here is, so basically dbScan cannot work very well in this case because each of our cluster has very different like density values. Okay, so in this case they cannot capture those data at a different levels of densities depending on different clusters. I mean, dbScan cannot work on these cases. But this is also generally a problem. I mean, I don't recall or I don't remember any kind of algorithm that can properly handle this kind of issues. Okay, varying quality or varying density of our clusters. And also, in general, it's quite sensitive to our parameters, depending on the epsilon value and the number of, the mean number of points. We may have a quite different cluster results. Okay, and then let's see. So previously we studied yeah, k-means or hierarchical clustering, and also in the case of hierarchical clustering, we use 4 different versions of computing the distance measures, right? So if you recall, yeah, we learned like a complete linkage or single linkage or maybe average linkage, and there was a fourth one, right? But yeah, so I want to ask the question of, yeah, in this case, so if you assume or if you imagine hierarchical clustering is being applied here, and then what type of a linkage or what kind of distance measures between the clusters and the points will work or will form or will generate this kind of cluster shapes. So yeah, let me just simplify the question. We had among the 4, we had a complete linkage and the single linkage. Which one will work or generate this kind of shape of the clusters? Single? Let me do a poll. Single or complete linkage? Do you guys remember the difference between the two? So in the case of a complete linkage, we are considering the worst case, right? So we had one cluster here, and then we have another cluster here, and then in order to merge this cluster to this cluster, we have to consider the largest distance, okay? And then in the case of single linkage, we are considering the best case. So that is the single linkage, and the complete linkage is yeah. So yeah, intuitively, complete linkage is connecting all the points to this point if we consider the worst case distances, right? And then all the distances between the other points to this will be less than this worst case distance, right? So that way we call that as a complete linkage. And then a single linkage is just the best case scenario, which is the shortest distance, right? And so yeah, so complete linkage will form this type of clusters, or single linkage. Okay, I think you guys got a good intuition. So single linkage will at least form this type of a cluster, right? Because in this case, if we formed this kind of cluster at first, and then when imagining the hierarchical clustering, we have, in order to merge this point, for example, into this cluster, we have to consider really large distance coming from here to here, right? So it will be really hard to merge this cluster into this existing cluster, okay? So that way, even though you may have thought the single linkage here is not a good algorithm, because it will generally form really large and unbalanced size of clusters, right? See. Okay, so we may see this a little bit balanced clusters, but in this case, it is showing really imbalanced clusters. When thinking about like 2 clusters, the left cluster is much bigger than the right cluster, and this is a kind of typical kind of imbalancedness that we often observe in the single linkage case, right? But sometimes single linkage, single linkage might be more suitable for your data. Okay, then in general, it's sensitive to parameters. So let me describe how you define these 2 parameters. So mean number of points and distance threshold. So it is described in the next few slides. But there is no really good approaches to determine properly this mean number of point and the epsilon value. But what you do typically is as follows. So you just set mean number of points, or maybe consider case nearest neighbor. Okay, case nearest neighbor. So if we set k as 4, and then for each point you compute its fourth nearest neighbor. So we had this point here, the first nearest, second, third, and the fourth nearest neighbor. And then what is the distance between them? Okay, and then if this point is really placed in the dense region, this fourth neighbor distance, fourth nearest neighbor distance will be really small. And then it might be, for example, maybe 0.1 centimeter. But if some points are really in a sparse region or not very dense region, and then its fourth nearest neighbor will have maybe the distance as 10 centimeter. Okay, and then you, if you have 100 different data items, and then you collect each point's fourth nearest neighbor distances, and then you sort them. Then you just draw them in a sorted kind of order. So in this case, so the shortest distance were found to be 0.01, and then the next shortest distance was found to be 0.02, and so on. And then if you see this kind of shapes, and then what it means is among 3,000 data items in total, majority of the data, for example, 2,800 data items, will have almost equal distances as fourth nearest distances. Okay, and only like 200 data points will have really large distance as fourth nearest neighbor distance. Okay, so if your graph is showing this kind of pattern, then you can kind of regard or consider maybe 200 data items as outlier or noise point. And then if you set the radius or epsilon value as maybe 10, and then most of the data points will be covered or included in your in one of these clusters. Okay, so here the main point is, out of 3,000 data items, you want to have majority of the data points to be included or contained in one of the clusters. So if it is generating maybe 3 clusters, and each of which is containing only 100 points, and then we may see only 300 data items were clustered out of 3,000 data points, which means 270 points, or maybe 90% of the data were regarded as a noise point. Okay, so that's certainly not a good parameter selection. Okay, so so this is how we determine our parameters. So we basically identify this kind of elbow point, where all the distances of a fourth nearest neighbor is staying as just a flat, although they are sorted. So they are monotonically increasing, but the increasing rate is really staying really low, and then it's drastically increasing after a certain number of data points. Okay, so we seek for this kind of threshold point or this kind of elbow point. But what about the number? So in this case, k is also set as 4. Then when k is set as 4, and then the corresponding epsilon value or the radius is set as 10. And then, so what you do here is, so you generate this kind of graph for various k values. So you generate this kind of graph when k is 1, 2, 3, 4, and so on. And then, so you want to find a good combination where this graph pattern has really clear elbow point shape. Okay, and in some cases, if k was not properly selected, for example, k was 10, and then the 10th nearest neighbor and its distance is in an increasing order will be having this kind of shape. In this case, we cannot clearly see any kind of elbow point here. So it means k is not a good selection. Okay, k is not reflecting a kind of a good value for your data. yeah, so you generate basically this kind of graph for various k values, and then find the clear elbow point, and then corresponding k values as well as the threshold values. Okay. Yeah, and then I think that's it for this DB skin. Any questions?
그 저거는 그러면 무조건 노이즈가 어느 정도 끼어 있다라는 전제 하에서
그렇죠. 네. 그러니까 이거 같은 경우, yeah. So I think the main practical benefit or advantage of this DB scan as a clustering algorithm is that it doesn't try to cluster every point into one of the clusters. Okay, in the k-means or Gaussian mixtures or what else? Yeah, typically any clustering method will generally try to assign every point into some of the clusters. In this case, we can naturally exclude some of these data points that are not belonging to any of the clusters. So that way, we can maintain the high clusters of the resulting clusters. I mean, high quality of the resulting clusters. And then also, another benefit of this clustering algorithm is that it can identify this this nonlinear shape of the clusters. So this is another clear benefit of this clustering algorithm. Yeah, and yeah, so I think this is another benefit of the cluster. Yeah, this DB scan algorithm to identify this nonlinear shape of the cluster. So people played with a lot of different shapes. So if you saw in the earlier cases, so this kind of weird shapes are properly clustered as well. Yeah. So for example, if you use a Gaussian mixture or Gaussian mixture or k-means, you
입실론이 정해졌을 때 입실론을 정할 때는 K가 정해진 상태에서 구하는 거잖아요.
네.
K를 정할 때도 입실론이 정해져야 될 것 같은데 서로 어떻게 이렇게 조직할까요?
이게 이제 아까 이제 여기서 그러니까 이거 뭐 완벽한 방법은 아니고요. 여기서 이제 이야기했듯이 이제 K를 뭐 1부터 그러니까 K는 사실 크게 어렵지는 않아요. 그러니까 무슨 소리냐면 K는 좀 다양한 어차피 인티저니까 시도를 해볼 만한 여지가 좀 많이 있어요. 뭐 예를 들면 저기 엡실론은 뭐 저기 뭐 10.1이어야 될지 9.99여야 될지 아니면 9.99여야 될지 이런 컨티뉴어스 밸류는 좀 더 뭐 하여튼 더 고라프고요. 이런 그래도 정수나 이런 디스크릿 밸류는 훨씬 더 파라미터 옵티마이즈 하기가 조금 더 쉬운데 이건 so I'm saying that we have two parameters, one being continuous variable and then the other is integer variable. So the number of mean number of points is a discrete value or the integer value. And so the strategy again here is so we vary or change or we basically try different values of k and then generate this kind of graph. Okay, so we can imagine this kind of graph for when k is 1 or 2, 3 and so on. And then we pick up the graph that will show this elbow point pattern most clearly. Okay, and that graph and the corresponding k value will be our selected k value. And then this kind of elbow point and the corresponding distance value, and that is our epsilon epsilon point. Epsilon value or the radius value. 답이 됐어요? 네. 오케이.
그러면 아까 DB 스캔 같은 경우는
네.
가 안 된다고.
네.
근데 뭐 GM이나 이런 건 어떤 형태에 따라서 안 되는 거 같지 않습니까?
네.
그 두 개는 그걸 다 커버링 해주는
네. 일단은 GMM 같은 경우는 덴시티 측면에서는 조금 이렇게 좀 숨겨도 돼요. 그죠? 아까 그 저기 코베리언스 그게 좀 넓게 잡히면 내가 이제 넓은 부분을 커버를 하겠다. 뭐 이런 게 되는데 이쪽은 이게 그게 안 되는데
그 다른 알고리즘
그 두 개를 뭔가 합치는 뭔가요? 사실 이 알고리즘을 조금 좀 어댑티브하게 바꾸면 또 가능할 수도 있을 것 같고요. 그래서 사실 이게 여러 가지 아마 시도들이 있을 것 같은데 여기서 좀 뭔가 엡실론과 네, 그러니까 뭐 엡실론을 뭐 1cm를 정해놓고 거기 안에 들어가야 되는 포인트를 뭐 한 원래는 한 K 그 민 넘버 포인트가 5개여야지 좀 적절해 보이는데 한 10개 아니면 20개를 잡아서 일단 이 알고리즘을 돌려요. 그러면은 대부분 다 노이즈로 취급이 되겠지만 거기서도 여전히 찾아지는 클러스터가 있을 거잖아요. 그러면 뭔가 걔네들은 따로 이렇게 빼놓고 어떻게 보면 네, 여기서 좀 이렇게 기준을 좀 이렇게 좀 굉장히 스트릭트하게 둬서 먼저 얘네들을 찾고 그다음에 얘네들을 다 빼놓고 우리의 이런 셋 어떤 데이터 스트럭처에서 나머지들에서 또 찾되 좀 이 기준을 좀 완화시켜갖고 혹은 파라미터를 좀 바꿔가면서 이제 할 수가 있을 것 같아요. So the question was, how can we handle this different levels of density values underlying in our different clusters? So I mentioned about the possibility of hierarchic or adaptively finding the clusters. So for example, we set the mean number of points as really high. So given a 1 centimeter threshold or radius, we set the mean number of points to be maybe 100, which is really large. In that case, those clusters will still be identified or will be obtained. And then we can set them aside as a kind of high quality clusters. And then we will still have a kind of remaining point, okay, among them. So all of them are considered as a noisy point when applying this parameter, but we just relax our condition as a cluster quality, or basically decrease this value, and then we keep running this algorithm again. And then we will find this a little low density clusters as well. Okay, and then and then also in this case of a clustering algorithm, so if you think about the main difference of this type of an algorithm compared to K-means or a Gaussian mixture model or even a hierarchical clustering model, is that it is actually obtaining the clusters one by one. Okay, so we obtain one clusters at a time, and then it's a kind of greedy method, right? So among our data item, we first obtain one cluster, and then we exclude them out from our data, and then from the remaining point, we find the second cluster, and so on. So this kind of approach has been quite effective, and if you're interested, this is another quite interesting algorithm called a bump hunting. So this was invented by the Stanford statistics guys, who are all professors in statistics department, and so if anyone asks what kind of book that I used to study machine learning myself, I think this book is quite comprehensive, and this book helped me the most, at least to me. And so so this is written by Trevor Hasty and Tibor Shirani and Jerome Friedman, and they are inventor of decision trees, for example, and random forest, and probably gradient boosting trees, which were the most successful classification method in my opinion. Prior to deep learning area, and still these decision tree based methods will work best when your feature is not that low level. So if you already obtained the high level features such as not just the pixels or just the characters in the language or just a word, which doesn't seem to be directly helpful in the particular classification tasks. In such cases where your features are really low level and the helpful informations are scattered around throughout these many different low level features. In that case, deep learning will be really effective. But if you collected really high level features that are directly helpful to classification methods, and that I personally think that deep learning is not a solution. So in that case, decision tree based methods such as random forest and the gradient boosting trees are one of the most effective methods. I mentioned this book, and the author of this book is because they also invented something called a bump hunting, and and also if you are interested in this book, and then this book is quite in depth. I mean, it's a quite difficult book, so their students. Their graduate student, their former graduate student who studied, who did a PhD with them, also. Oh, wow, it's interesting. Wow, how come they complete this kind of queries? Because it's taking into account the previous queries, right? Wow. Anyways, so this is a undergrad level of the same book. Okay. Yeah. Okay, and related to this bump hunting. So bump hunting is also, I think it's related to some active research area within data mining area, which is called K-core. K-core, finding K-core or something like that. So K-core means, or this bump hunting, as personally I think they have the same idea, and this is I'll describe them as follows in just briefly. So it's still an unsupervised learning, but it's based on kind of density estimation. So given a bunch of the data, so you estimate the density, okay? And then if you modeled your density as your Gaussian mixture model, and then you will have a complete description of these how this density is formed, or how this density is looking like in the entire regions of your feature space. But given your full description of your feature space in terms of your density, then the practically useful task will be to identify some subsets or some regions in your feature space that have high density of your points. Okay. So in this case, so let me try to give a practical examples. So so suppose you collected all the people that has a certain disease, okay, and in that case you found some basically they are just you can view it as a kind of clustering algorithm, okay, but these are like finding some partial clusters around among your data. So you want to have really high quality clusters that are kind of really dense and cohesive within a single cluster, but not involving many other data items. So in the case of density Gaussian mixture model, in this case you may have one single cluster and then the other cluster here, okay? And then what if we just apply some threshold to have some high density regions, okay? So for your cluster, you want to maintain the minimum amount of minimum quality for your cluster, okay? So what is that density sub-region? I mean the sub-region that has the kind of minimum density of those data items. In that case, you can view, or in the context of a patient data that has a certain disease, okay, some patterns, or it can be viewed as a Oops. So if you worked on this bioinformatics or medical informatics domain, there is some term called a phenotype. Phenotype means some representative patterns that has some certain disease. Okay, so if a person has around a 1 centimeter tall and then maybe 100 kilometer as a weight, and then these people will have a really high probability of having a certain disease. And then for the same disease, maybe I don't know how much it makes sense, but 190 centimeter and also maybe 70 kilogram. Okay, if those two conditions are met, I mean, I'm talking about some kind of approximate sense. And in that case, it will also have a high chance of having that disease. Okay, in that case, if we can have this kind of list of these combinations of our features in terms of their regions, okay, and then it will work as a kind of good list of our candidates, okay, that we can use to map as the group of a particular disease. Okay, so in this case, it is called finding some subset of the regions. So it's rather than finding the data subset, it's more about, so its output is more about the description in terms of the feature space. So instead of out of these existing data, those are one clusters and those are the other clusters. Instead of describing our clusters in that manner, we can describe these clusters as 170 to 175 for the first feature, and then the second feature is around 95 to 105. And then it might have another features as a additional constraint. So if you describe a subset of your data that has a high density corresponding to particular labels, and in that case it's called here we call bump, or in the data mining this is also quite actively studied area, which is called a K-core algorithm or K-core identification or something like that. Okay. Okay, so in this case, why we call this as a bump hunting is because in terms of a density, so we are finding some sub-regions that has a high density. So in that case, the highly dense regions can be viewed as a bump, right? So that way, we are saying this as a bump hunting algorithm. Okay, so most of these algorithms are done in kind of a greedy manner. So they try to find one bump or one of this K-core type of region one at a time. Okay, so these are kind of interesting or practically useful kind of data mining tasks. Okay, so although these are not actively studied in the machine learning or deep learning or artificial intelligence, but these are often quite useful in real-world tasks, and so these are kind of one of the few data mining exclusive areas, I think. Okay, so among many different areas that have high overlaps between data mining, machine learning, artificial intelligence, and so on, I think this is a kind of one exclusive area in data mining. Yeah. Any other questions? Okay, give me just 1 second. Okay, then the next chapter is also about the clustering. So we will cover, I think, two different methods. based on some matrix factorization. And the first one is called a NMF, and I believe my own student will be quite familiar with this kind of method because I do a lot of research based on it. And this is quite a linear algebraic kind of context. And then the other one is called a spectral clustering. Yeah, so this spectral clustering was once, it was a really popular method in the context of clustering. Yeah, so it's roughly having including this tutorial and then another theoretical papers. Yeah, it's more than 10,000 citations as well. So I think it's worthwhile to study. I think. Yeah. So I guess there are many chances or opportunities that you will learn about the deep learning, but sometimes I think you don't find much opportunities to learn like traditionally popular methods as well. So yep, and I'm curious about NMF as well. Yeah, so NMF has also about this many citations, and also it doesn't show up the Nature papers. Huh, it's interesting. Yep, this paper. Yeah, so this paper is the representative paper for NMF, and also the other paper published in NIPS in it was published in 1999, and this paper was published around that time. So it's also cited in total more than 10,000 times. So we are studying those methods that okay. So the first topic is an NMF, or non-negative matrix factorization. So we discussed about like two different types of an input when running the machine learning methods in general. So the first one is the feature vector representation, and then the other is the graph kind of representation. So for example, pairwise distance information, or pairwise similarity matrices. Those kind of inputs are one form, and then the other one is feature vector representation, where each column or each row can also be data item, but let's use each column as one data item, and then each row will represent one feature dimension. Okay, in that case, in the case of non-negative matrix factorization, we assume that our input matrices are all non-negative. So each value will have non-negative value, and then given this non-negative matrix as our feature vector matrix, collection of feature vectors, we decompose it into these two matrix that have lower ranks. Okay, so this is a basic form of an NMF. And then rather than being a clustering method, it is just a general matrix factorization method, and also you can view it as a dimension reduction method as well. Then we can further utilize this dimension reduction method as a clustering method. And also, let's see. And then in this case, given maybe 100 data items, we are generating, or we are setting the rank to be 5 in this case. So we are having 5 columns And then, so let's use a particular numbers. Then let's consider 100 features, and then 500 data items. And then we are decomposing that matrix into rank 5 matrices. Then each of the W will be 100 by 5, and then H will be 5 by, or 500 by 5. Okay, here in this non-negative matrix factorization, given non-negative input of our matrix, our W and H, every element should be non-negative. Okay, then we want to minimize the difference between this input matrix A and then the product of these low rank matrix W and H. Okay. And then in terms of the one single quantity that defines or that measures the differences between these two matrices A and WH, we can use the Frobenius norm, or another popular measure is K-R divergence. Okay, so in this case, in the case of a Frobenius norm, we have a matrix here, and then we have this product of these two, and then we just measure the difference of each value. Okay, and so and then we okay, so we have a big matrix, and then this product of matrices. Then this guy was originally 3, and then if we multiply these two, then this will have the same size of matrix A, and then this guy was, for example, 5, and then it has the difference of 2. And then we simply take the square of it, and then if it was 2 and then it was 1, and then it also incurred the difference of 1. Then we just simply take the squares and then sum them up. So this is the measure between these two. Okay. Then we just minimize them. We want to minimize them by carefully setting up or determining each values in our W's and H's. Okay. And then the K-R divergence form of the measure is written as follows: W times H, and then the original matrix A. Okay, so in this case, we view this matrix A as similar to TSNE. We can just simply normalize matrix A so that the entire sum to be 1. In that case, we can call this matrix A as joint probability. Okay. And then we will have W and H, and then we also normalize this W and H so that their sum becomes 1. And then we can just write the difference between these two joint probability distribution as using a K-R divergence formula. Okay. Although I personally don't use this K-R divergence as objective functions, but this is another stream of research in this non-negative matrix factorization, or simply NMF. Okay, so we can view this we can set it up. We can set our objective function as either purely this matrix sense as a matrix norm, which is a K-R divergence in this case, or from the probabilistic sense, we can use this K-R divergence sense. And also, you know how this K-R divergence works, right? So it is like, so if this probability was 0.1 and then 0.05, and then we bring this as our weight factor, and then we compute the log version of these two probability of this guy and this guy, log 0.05. And then we measure the difference in terms of log versions of the two probabilities, and then we weight them using the original probability. Okay, so if we have a high probability originally, then we want to preserve that with a higher weight. Okay. Okay. And then, so let me contrast the main kind of difference of an NMF, or non-negative matrix factorization, compared to another quite famous matrix factorization called a principal component analysis. Okay, so so let me describe this figure, which is called a it was once quite popular technique called the eigenphase. Eigenphase. So this is a quite cool name, right? So today I feel like searching for Google Scholar and check the citation, but let's check the citation as well. Okay, not much. Yeah, I think the title itself didn't contain this eigenphase, but yeah, there is a paper in a TPAMI. Do you guys know about this journal, TPAMI? Oh, yeah. See? Yeah, I only search for the papers that have at least 10,000 citations. Yeah, so this was once really popular and popular technique in the facial recognition. Okay, eigenphase and a Fisher phase. So Fisher phase is from the linear discriminant analysis that we already studied, right? So eigenphase is just an application of PCA in the facial recognition applications or data, and Fisher phase is just a application of the linear discriminant analysis in the facial recognition data. Okay, and just to let you know, this TPAMI is a top journal in the, I think, arguably the best journal in the machine learning, which is a IEEE transaction on pattern analysis and on machine intelligence. This is a really prestigious journal. Yeah. But anyways, so back to this slide, what it did was as follows. So we collect all these facial images. Okay, so suppose we collected all your facial images as a picture, and then suppose that image was represented as maybe 28 by 28. Okay, and then you just collect, you can just slice vertically all these pixels and then concatenate them, and then construct a single really high dimensional vector, and then maybe we collected 10 pictures from each person. Okay, and then you just apply the PCA, and then we have 384 as a dimension, and then maybe suppose we have a 30 person, and then maybe 10 images per person, and so we have 300 pictures, and then we just do the PCA. And then PCA will do this kind of low rank. Okay, so this was 784. Okay, thanks. So in this case, although we have the diagonal matrix in the middle in the PCA, but usually when applying PCA as a dimension reduction method, we include this guy into the right part, right? Okay, and then what is this showing? So this becomes our basis vectors. Okay, so let's think about a little bit of a linear algebra. So suppose we collected maybe 3 columns. Okay, and then we have 300 column vectors here, And then each column vector will be represented as a three-dimensional vector, right? And then, yeah, in terms of a linear algebra, the first column here, or this is corresponding to a particular facial image, okay? And this image will be represented as a linear combination of, so let's see, let me just clean here, and then the linear combination coefficient here was -1, 2, and 1. So in this case, what it means is, so it is used as a linear combination coefficient corresponding to each of our three bases, right? So that's how we linearly combine these three bases in order to reconstruct this particular image, right? Then what about the second one? So we have a second vector, and then for that we will have another linear combination coefficient like this. And then using these different set of linear combination coefficient, but using the same basis, we have to reconstruct this kind of particular images, right? So we have to do this kind of reconstruction on all these 300 images. Okay, so that way naturally those bases, three bases. So usually the number of these bases are much smaller than these number of columns that we have, or our data items. Okay, so in that case, these three columns should be formed so that they can maximally describe or explain all of these 300 data items. Right? So that's how these bases, or three bases, are extracting out as common as possible patterns in our data. Okay? So that's a kind of intuitive understanding about this PCA, or this kind of general matrix decomposition. And then when applying PCA into this 300 facial images in this as this pixel representation, they will give. So if we used maybe 1, 2, 3, 4, 5, 6, 7, 7 by 7, which is 49 bases. So here we use the 49 bases, and then each of these images are the reconstructed images by just extracting out each of these columns. So this column is corresponding to this, then the second column is corresponding to this. Okay, then so this guy, the middle one, is just a linear combination coefficient corresponding to each of the bases, okay, in order to reconstruct one of the 300 images. So you can, this image on the right is the one particular image, one particular facial image, and then these are the optimal coefficient by using this common basis. Okay, so you guys understand this figure. Okay, so in this case, so how we color map different values into here is, for example, the red color is like the most positive value, and then this black color is the most negative value, and then probably the white value is representing 0. So that way, that's how we color map or color encode different quantities into this color map. And then also we use the same thing in here. And then as we can see, these bases are not very interpretable, right? But at least this is called a feature. This is called eigenface. Okay, so eigenface is just nothing but a reconstructed image of a PCA basis applied to the facial image dataset. Okay, and then also in the case of applying LDA, when the class labels are available, in that case we can do exactly the same thing, right? We can collect those basis vectors extracted out from LDA or linear discriminant analysis, and then reconstruct them into these images. And in that case, those basis images will be the common basis that will be most helpful in discriminating or separating out between different clusters. So that is called this a feature face. Okay. So in the traditional, yeah, it's published in 1997. So back then, this was considered as a kind of state-of-the-art facial recognition technique. So here, what we do is, so we only use this limited number of bases, and then hopefully the remaining bases are just containing only those noise data, which is not helpful, or which is actually hurting our classification performances. Okay, so that's how we kind of throw out those noises contained in those minor dimensions identified by PCA. So this is really simple step. This is just a simple pre-processing, but that was quite popular, and also even has a really nice name of eigenfaces and feature faces. Okay, then you now understand this figure, and then let's try to do the same thing on the NMF. So again, in the case of an NMF, so here in this case of PCA, we both involve positive and the negative values in this basis part and also this coefficient part. Okay, but it sometimes doesn't make much sense. I mean, intuitively, by linearly combining these different bases. So what does it mean to just linearly combine these different bases with a maybe positive and negative bases? So we are subtracting some facial bases, right? And so it doesn't make much sense. But back to this NMF thing. So NMF is doing the exact same thing, but our bases are all non-negative or 0 or positive, and also linear combination coefficient that construct each of our images are all positive values or 0 or positive values. So in that case, our words are only allowing the addition. So in that case, it's much kind of intuitive and interpretable, and more interestingly, the resulting basis. So here, so if we perform the NMF, and then we brought this to reconstruct them as just this kind of images. Okay, image reconstructed version of the NMF bases are interestingly showing these part-based images. So it is surprisingly identifying or revealing some some mouth and nose, and maybe some mustaches and eyes and so on. Okay, so and also a particular image which is reconstructed by linearly combining all these bases only using non-negative weights. So we are only allowing adding those bases. Okay, so that way we are not considering the subtracting, for example, subtracting nose, okay, from some particular images. What does it mean? So we are removing such kind of situation. That way we can kind of improve the efficiency, and also surprisingly, or in terms of the quality of the revealed bases, they are revealing this kind of part-based basis. Okay. Yeah. So using just one single figure and really nice, just a gradient descent based update formula. Those guys who are all kind of Koreans, they published the Nature papers. Using just a single figure of this, I think. Okay, so this is a NMF. Let's see. Then let me discuss or describe how this NMF is used in the clustering. 네.
그 그레디언트 디센트로 학습을 하면
네.
그 non-negative라는 컨스트레인이 있어야 되잖아요.
네.
0보다 작아지는 클리핑을 하는
Okay. So the question is, we have to consider the constraint of where we have to maintain all the resulting values to be non-negative. So in that case, what if our gradient says we have to make our value to be negative? So in that case, we just we maintain them as just a zero. So it's like a clipping, right? Or just blocking the values not to be negative values. So in that case, we call that method as something called projected gradient descent. Projected gradient, descent method. And so projection means, so it is really based on nice optimization theory. So in the context of optimization theory, they often consider a constraint optimization problem. So if we don't have any constraints like a PCA, and then it's called a unconstrained optimization problem. But if we have some constraint on our variables, in that case we call them as a constrained optimization problem. And then in that case there is something called a feasible set. So feasible set means all the possible solution spaces, which is a subset of the entire space. So if we think about the non-negative solutions, and then the positive quadrant, is it the right name? So in the case of two-dimensional space, suppose our function is, so we want to minimize this function, and then what is the optimal value for x? We know this value to be -1, right? In this case, we have this kind of shape. But suppose we have this kind of constraint, okay? In this case, we know, so this guy, this part is called our feasible set. And then this feasible set can be in this simple form. But what about our feasible set to be linear, linear shape of x1 plus 2x2 should be maybe -5. Okay, so we can imagine this kind of feasible set as well, right? So in that case, the possible space of maybe not along the axis is like below a particular hyperplane, right? Okay, so that is the notion of this feasible set. And then the projected gradient means, so you perform the gradient descent update, and then you actually perform the projection as a post-processing from that solution. So you first perform the gradient descent using just the unconstrained situation, and then your solution ended up like outside of your feasible set. And then what is your so you actually perform the post-processing step that that makes this one be included again into our feasible set. And in that case, what you do is to actually do the projection. Okay, so projection. So typically, projection is done as a orthogonal projection, and theoretically that is often as a kind of optimal solution. So so suppose this was your feasible set, and then your solution was around here. And then after doing the gradient update, and then the new solution was here. And then what is the closest possible solution that are inside of your feasible set? And then you can basically perform this orthogonal projection onto your feasible set, right? So in that case, we basically do the projection, right, to make this guy come back to our feasible set. And also, this kind of feasible set can be linear, but in more complex scenarios, your feasible set can also be nonlinear. So what if your feasible set is maybe this, okay, inside of your circle? So in that case, the feasible, projecting onto this nonlinear set may be really be complicated process, right? So projection onto this shape may not be an easy problem. So so if you study optimization theory in more detail, you will see how this kind of thing is performed. So so in the case of an SVM, or if you study the deep learning, so you might be familiar with the gradient descent, and as a second order method, you might have heard about like LBFGS and something like that. And then there are many different optimization algorithms that tries to that tackles this constrained optimization things. And then SVM is one of the representative constrained optimization problem, because your regularizer. So you guys have a regularizer like this, right? So some hinge loss, and then some regularizer on your weight. Two norm is included in the SVM objective function, and then this this regularizer is like converted into this constraint, right? So if you remember this SVM, and then even though you may not have understood the full details, but sometimes this kind of regularization is the same as having some constraint where you only optimize or minimize or maximize this part, but this guy is converted into some constraint. So in this case, this is a one representative constraint optimization, which has this a nonlinear feasible set. So in this case, there are many different algorithms, and related to this projected gradient descent method. If you hear later about this method, trust region based method. I'm just throwing these terms. Trust region based optimization method or things like that. And this trust region is related to this feasible set. Okay. So I'm not sure how much it will help, but if you remember this in the later times, it might be helpful to have a big picture, or have a kind of guidelines on how to study, how you study on these topics. And okay, so in the case of back to this NMF, but fortunately, in the case of an NMF, the orthogonal projection onto this feasible set, because the feasible set for the NMF is really simple one. Okay, it's just a positive quadrant, just like this. So if you have solution here, and then the orthogonal projection from this point to the feasible set will be just this point. Okay, so it is just a simple process of clipping the negative values into 0. Okay, and then without giving much details, this Li and Seng, or Daniel Li and Sebastian Seng, or Sebastian Song, who is an author of Daniel Li and Sebastian Song, who are both Koreans, although they are, I think they are immigrants. So their parents are immigrants, and then they were born in the U.S. But what the advantage or one interesting thing of their algorithm, or the algorithm that they propose based on the gradient descent, okay, So projected gradient descent is one that they propose. So you should be able to easily understand the algorithm details if you look at these papers. But they actually manipulated some step sizes so that the update of the gradient descent is not based on some fixed step size, but based on some fixed multiplicative step size. So yeah, it is. Yeah. So let me just give a big picture or brief ideas. So if you perform the typical gradient descent, then you will update like this. So step size, let's call that as S, and then the alpha and the F, right? And so this is typical gradient descent algorithm, but somehow they carefully designed this kind of step size so that we have this kind of updating formula. So that way, instead of adding or subtracting some values, yeah, if you carefully define this step size, and then for this particular case of non-negative matrix factorization, it is formulated as this. So it is already a non-negative value. So in this case, we can maintain those values as all non-negative in every iteration, right? So if we add or subtract, and then it might become negative from positive values. But if we use this multiplicative form, and then if we start from all non-negative or all positive initialization, then all the values will remain the positive values. Okay, so that way, if you see this algorithm for non-negative matrix factorization, you often see multiplicative updating or MU algorithm. So that is actually changing in a nice form, in a nice manner, from this gradient descent update into this multiplicative form, which just multiplies some values from the old values. Okay, I'm not giving any details, but yeah, if you're interested, you can look at the papers. And I think time's up, so yeah, that's it for today. And then probably the next time we should be able to finish the remaining clustering chapters. Okay. Okay. Thanks. 네.
그 프로젝트 그레디언트 테스트가 좀 궁금한데요.
네.
이게 보통 그 컨스트레인 프로그램 같은 경우에는
네.
보통 뭐라고 해야 되나, 그러니까 라그랑지안을 사용해가지고
네.
약간 문제를 뭐 프라임을 듀얼로 바꿔가지고
네.
좀 푸는 게 많은데 이 방법론이 그러니까 뭐라고 해야 되나 하나의 그러니까 이게 일단은 처음에 업데이트를 하고 그 후에 그 피저블 셋에 프로젝트 시킨다는 발상이잖아요.
네.
뭐 어떤 장점이 있나요? 이 방법이?
나도 디테일을 잘 모르긴 하는데 일단 그레디언트 디센트 기반의 방식이라서 굉장히 간단하다는 거죠.
간단하다.
베리어블이 많아지면 사실 세컨 오더 기반의 방식들은 대부분 좀 잘 안 돼요. 그래서 그레디언트 디센트로 어떻게든 좀 해보고자 하는데 근데 그레디언트가 뭐 거꾸로 이렇게 발생이 되면 어떻게 할까요? 밖으로 벗어나면 어떻게 할까요? 뭐 그것들에 대해서 이렇게 좀
이것도 스텝 사이즈도 예민하죠. 이렇게.
그렇죠. 이제 스텝 사이즈는 일반적으로 전체적으로 조금씩 줄여나가는 식으로 많이 이제 알고리즘을 하고, 그다음에 저 스텝 사이즈도 뭐 이런 게 있어요. 룰이라 그래갖고 스텝 사이즈를 또 어떻게 R이 있었나 없었나 모르겠는데 이 아미오 이게 조를 요라고 있는데 아미오를 이렇게 해갖고 스텝 사이즈 자체도 좀 어떻게 이론적으로 좀 잘 디파인을 하고자 하는 옵티마이제이션에서의 그런 것도 있어요.
아 이렇게 하는 거 처음 봐가지고
네.
이게 되게 좀 흥미로운 것 같아요.
네, 뭐 재밌어요. 이쪽 공부하면 재밌는데 나도
네.
좀 잘 깊이는 몰라서.
네, 감사합니다.
네.
다름이 아니라
네.
템플릿 하는 거요.
네.
그 몇 명이 한쪽으로 짜요?
한 3-4명까지는 가능할 것 같아요. 네.
근데 정확하게 어떤 거를 우리가 준비해서 5월 1일에 발표하는지를 잘 모르겠어.
자유주제여서
아무거나요?
네.
정말 아무거나 아니면 관련 있는 아무거나요? 아니면
이거 뭐-
어떤 것에서 아무거나?
뭐 기본적으로 시각화 과목이기 때문에
시각화 관련된 아무거나요? 어떤 거든 상관없고.
네.
뭐 발표를 정확하게 어떤 거 하는 거예요?
프로젝트 프로포절 이제 다큐멘트를 한 장에 2장 정도 이제 써내고요.
네네.
A4 한 장에 2장. 그다음에
네.
그때 얘기했던 것처럼 그 하이마이어스 퀘스천이라고 했고 하이마이어 네 여기서 보면 여기에 있는
거기 있는 것
네네네
중에서
여기 있는
하시는
질문들을
거?
좀
네네.
명시적으로 좀 대답을 하는 형태로 발표가 이루어지면 가장 좋을 것 같아요. 네. 여기 보면 네 여러 가지 그런 게 있어요. 뭐 일부 프로젝트 프로포절의 경우 뭐 엄청나게 이제 많은 걸 이제 하겠다라고 이제 이야기는 하는데 실질적으로 이제 뭔가 의욕만 앞서고 뭐 어떤 구체적인 계획이라든가 시간 내에 뭔가 할 수 없을 법한 프로젝트를 애초부터 제안을 하게 되면 그런 것도 사실 실제로는 좀 문제가 많이 돼요. 그런 측면에서 뭐 리스크도 생각을 한번 해보고 얼마나 시간이 걸릴지 실제로
네네.
그런 것들도 한번
네, 알겠습니다.
네.
감사합니다.
네. 네.
어제 메일
네 맞아요. 내가
네.
너무 바빠갖고 아직 답시를 줄 시간이
아,
없었는데 일단은 내 저기 홈페이지에 저기 달력 보기가 있거든요. 스케줄민가 뭐 민민가 뭔가 있어요. 거기서 빈 시간을 저녁 때 포함해갖고 뭐 다 이렇게 해갖고 가능한 시간 이제 해갖고 찾아오면 좋고.
그럼 제가 메일 한 번 더
네, 그래요. 네.